high spin. So high spin is the direct opposite of low spin. That fourth electron now occupies the dx squared minus y squared in the EG set. This is when the pairing energy is greater than the octahedral field splitting energy. So it forces that fourth electron up into the EG set. Now, this is, as I said earlier, the high spin state. D electrons take this high spin arrangement when placed in a weak ligand field. Some ligands split the d orbitals on a transition metal cation very poorly and always lead to this high spin state. Interestingly, there should be a difference in the number of unpaired electrons between a low spin state and high spin state. Notice that the low spin arrangement has only 2 unpaired electrons, whereas the high spin state has 4. The number of unpaired electrons affects how the ion, or in this case the compound, reacts to a magnetic field. There are a set of factors that affect spin state, and you'll need to know these. First is the geometry of the ligand field. First, octahedral and square planar complexes can give either high spin or low spin states. However, with tetrahedral ligand fields, you always get high spin states because of the greatly reduced crystal field splitting energy, delta T. The second factor that affects spin state is the oxidation state of the metal cation. The higher charged transition metal cations lead to greater crystal field splitting. So if you looked at Ti2+ versus Ti4+, you would expect Ti4+ to have a greater split of the d orbitals. The greater the charge, the stronger the ligands interact with the transition metal center, and therefore the d orbitals split more. Third is the size of the metal cation. If you have larger metal cations like those in the 4d and 5d rows, they're going to interact with the ligands more strongly, split the orbitals more effectively, and you're going to generally have low spin complexes. Also, the transition metal d electron counts can affect whether you have a low spin state or a high spin state. Let's look at the fourth factor now and see how it affects whether you have high spin or low spin. So if we look at electron counts where they're D0 to D3, so that's what I'm showing in the 4 respective boxes here. Of course, D0 has no spin state since it has no electrons, but D1, D2, and D3 always have high spin electron configurations because these electrons are never in the EG orbitals. They never populate because you don't have enough. Up to 3 electrons must always populate the T2G orbitals. It gets a little more tricky when you go from D4 to D7 electron counts on your transition metal cation. You can see either low spin or high spin. I'm showing the low spin configurations here on this slide. Notice that I've also included the number of unpaired electrons with each of these orbital sets. So for a D4 cation that has a low spin electron configuration, notice that you have only 2 unpaired electrons and that there is 1 pair of electrons in the dxy orbitals. For D5, you have 2 pairs of electrons occupying the T2G orbitals, leaving only 1 unpaired electron. In a D6 electron configuration, you have all 6 electrons paired up in the T2G orbitals, leaving 0 unpaired electrons. And once you get to D7, you have 1 unpaired electron. And that's because the first electron occupies the EG orbitals. So let's look at the high spin configurations for D4 through D7 electron configurations. If you have a D4 metal cation, guess what? You've got 4 electrons that are unpaired because each orbital has 1 electron in it, except the DZ squared, which has 0. D5 gives you 5 unpaired electrons, clearly showing that there's 1, 2, 3, 4, 5 electrons in each of the 5D orbitals. Now, when we get to the D6 electron configuration, we must start pairing up electrons because we've run out of empty spaces. So, we come back down to the bottom and start with the DXY and put the first electron, or the 6th electron, in there. This gives us 4 unpaired electrons. And in the D7 metal cation, notice that there's only 3 unpaired electrons because there's now 2 sets of paired up electrons. This is in contrast to what you see earlier. For low spin complexes, a D4 cation would have 2 unpaired electrons. For a low spin D5 complex, you would have 1 unpaired electron. For a D6 low spin complex, you would have 0 unpaired electrons. And for a D7, you would have only 1 unpaired electron. Now D8, D9, and D10 are always low spin, always, because you fill up the T2G and you just finish filling up the EG orbitals starting with D8. So, with the D8 metal cation, you have all 6 spots occupied in the T2G orbitals, and you have 2 unpaired electrons in the EG, so D8 cations always have 2 unpaired electrons. D9 has all 6 electrons in the T2G set paired up and 1 pair in the EG set. There's 1 unpaired electron left, so D9 has 1 unpaired electron in a low spin electron configuration. And D10, all 5 orbitals have 2 electrons in it, leaving 0 unpaired electrons. If we think about magnetism, D10 or D10 electron configurations are always diamagnetic. Low spin D6 electron configurations are always diamagnetic. And D0 must always be diamagnetic. The rest can be paramagnetic. Now, let's continue to think about crystal field stabilization energy. Let's go back to the 2 different ways that you can arrange 4 electrons in the d orbitals. Remember, there's 2 possibilities. You can put all 4 electrons in the T2G set, giving 2 unpaired electrons. The second possibility is to put the 4 electrons in their own individual orbitals, 3 in the T2G, 1 in the EG, leading to 4 unpaired electrons. Now, we need to think, which of the following possibilities is energetically favorable? Because there's really 2 possibilities here, but one must be favored over the other.